Okay, good afternoon, 61C. Good afternoon, 61C. Wonderful. Okay, so today we're going to keep going through hardware design. So last time we took a look at basics of transistors and how you turn them into logic gates. We started looking at combinational logic and how you build it, describe it with truth tables. Talked a little about logic expressions and how to simplify them. Today's lecture, we're going to be going on to building more complete systems. We started looking at this last time. So as a reminder, we're down in this hardware level now, working with your real devices, real physics, and building logic out of them. So this is a very key thing you're going to have to really drill into your head. When you're building digital systems, the kinds of circuits divide into these two types. Question? Is the mic on? Can you hear me? Nope. The light is on. Hello? I don't think it's on. They drive that up there. Hello? Is it coming on? Let me try the other one. Hello? Okay, can you hear that? Is that better? Okay, so when you're thinking about digital systems, it's really important to divide the circuits into these two camps. Combinational circuits, which actually do all the computing and munge the bits together to give you new results. And sequential circuits, which basically store data over time. So they can hold on to data and keep it for a period of time. So it's combinational logics with SL, sequential circuits, sequential logic SL, right? CL and SL. So state elements, we use these to store values for later use. You've kind of seen this already in the register set for MIPS, $1 through $31. Those are 31 registers, each of 32 bits. Also the memory in the system, the cache is the main memory. There's also state elements. As well as use them to store information. In this way, we also use them to separate waves of signals propagating through the digital logic. Remember, a circuit is a massive parallel array of wires and gates, and it's all doing stuff all the time. It's like the real world. Everything's happening. You guys are all, you're reading Facebook over there, you're listening over there, you're chewing something over there. It's all happening in parallel across a lecture theater, right? It's not like one at a time you guys are doing stuff. I'm not running a sequential simulation of each student. You're all doing all your stuff in parallel all the time. That's the way hardware works. And to synchronize it, we use these register elements as well. What happens is they remember the input value at some point in time when the clock arrives, and they're going to hold on to that value and keep propagating that value until the next clock edge arrives. So we kind of synchronize things on clock boundaries. So the way to think about this parallel circuit, the circuit is a large parallel system. We actually have to enforce some sequentiality by adding these state elements in places to make it work correctly and allow us to reason about it. So this was the example we had right at the end of the last lecture. It's kind of noisy from the guys freaking out about the 70 midterm outside, so I'll go over this again. You guys, of course, will not freak out about the midterm next week. So remember this example. We're building an accumulator. So what the accumulator does is read a string of values and sums them up. If you're writing this in the C program, it'd be a very simple loop, the loop shown here on the slide. S equals 0 for I equals 0 through n minus 1. S equals S plus Xi. Very easy. And after you're done, the sum is available in the output S. Okay, so that's a very simple accumulator example. But without sequential logic, we can't really make it work. So if we just have combinational logic, I just build an adder circuit and kind of try and wire the output back to the input, it doesn't really make sense, right? So remember, a combinational circuit, just flow, the values from the inputs flow through the circuit to the output. You're basically turning those transistors on and off, connecting power and ground to the output. So in this case, you have this feedback, but it's not going to work because, for one thing, you don't get to say when does the next value show up and get added in. There's no sort of notion of when the input changes from the old value to the next value. And also, we can't initialize this and say the initial sum should be 0. There's no kind of way of saying that in this simple circuit. So we add a register. So thing to emphasize again, the register here is a storage element, but we're not really using it. We're using it kind of to store the value of S. But more importantly, it's breaking that feedback loop and making a more orderly progression of signals around the circuit. So this register here has an input and an output. And this little diamond triangle symbol here is the standard notation for where the clock arrives. So when the clock arrives and there's a positive edge on the clock, the function of this register is to copy what's at its input to its output. And after that rising edge of the clock, it retains that value. It doesn't change. No matter what happens here, in between the clock edges, this output is stable. All right? So the clock signal, the important function of the clock is to tell everybody when to sort of move to the next step. So you're broadcasting this square wave around the whole system. It's going to all the registers and signifies when all of them sort of jump to the next step in the system, in the execution, right? I don't know why this one is on the falling edge. Okay, it's on the falling edge. It doesn't really matter. So these falling edges are going to be when things happen. And so on the output S, what we'd like to have happen is, X0 appears. Here, you read in X0. There's nothing to add it to, so you output it in the next clock. After this clock edge, X0 will appear here. Then you want the sum of X0 plus X1, then X0 plus X1 plus X2, and so on. So remember, this signal notation here is saying there's some multi-bit bus. So there's multiple bits. So this little dash across the line indicates there's more than one bit in that wire, right? That's a standard, double E schematic notation. If you have a wire, kind of assume it's one wire, unless you see this dash across it, which says it's multiple bits. And usually you would sort of write here, say 32, to indicate there's 32 copies of one-bit wire. So it's actually a 32-bit bus. So that little diagonal dash is a standard notation double E's use. All right, so say this is a 32-bit bus here, carrying 32-bit individual signals. And this is just showing you the value on that 32-bit bus. And each of those individual bits may be ones or zeros. So that's why this waveform kind of has both the top and the bottom drawn in, right? Because any individual bit may be 1 or a 0. And then at the clock edge, notice they all swing, and some bits swing from 0 to 1, some from 1 to 0, some stay at 0, some stay at 1. So you just kind of draw that as a vertical line here. That's the notation. And thing to realize is that where is X in here? Well, X is set up. You have to set up this value ahead of time so that it flows. You set up the voltages at the input of this circuit. The circuit settles down into a stable state. That's reflected here. Then it's ready at the input of this register. Then at the clock edge, you clock it in. And so if the input to the register is X0, the output will be X0. Actually, this is showing you the value here. So initially, this is 0. So 0 plus X0 is X0 here. So this is showing you the input to this input here, the whole circuit. Once we've clocked in, at this point, once we've captured the first value, it's then safe to change this input to the next value, right? So we've captured the first iteration of the loop, where sum equals X0. Now we can change the input to the circuit. Here, X0, we change it to X1. So we're moving these bits around here from X0 value to X1 value. And that's okay because this register prevents this output from seeing any changes here. So as soon as you start changing these bits here, this circuit may start changing the bits here. It's going to start changing towards being the next sum, which is the value in this register plus this signal here. So X0, which is captured in the register here, right? And that's here. This X0 was captured into this register. So this X0 value is coming out of here, being added to the X1 value, and you're forming the next sum, x0 plus x1. So these lines are waggling around. Actually, that's not shown here. It'll eventually then be clocked into this register at the next clock edge to form x0 plus x1. So as soon as you start changing x1 here, the adder starts creating the next value here. All right? So having that register there gives you that timing moment where you know it's safe, when it's safe to change the input, when it's safe to read the output of this device. And the register just holds its input until the next clock edge. So this is a very simple example, but all digital systems basically boil down to the same model of you have registers separating combinational logic. So registers hold the sort of inputs, hold the input stable for the next clock cycle. Once the combinational logic evaluates the next values, you capture it in the register. And the register then takes a snapshot of the input values, and then after the clock edge, sends it out on its output bus, right? So you have this sort of lockstep movement in the whole system. So any big synchronous system, you break up into combinational logic blocks separated by registers. And all the registers are being clocked by the same clock signal. So then, from outside the circuit, you're having some inputs arriving, which are being processed by the combinational logic to produce the next values. Okay. So these registers, the ones we're using are called flip-flops, and they're called flip-flops because the output can go from 0 to 1 on the clock edge. They kind of move up, move down, or stay where they are. But they only change at the clock edge. So it's like taking a picture of the input. You take a snapshot of the input, and you hold it. And that's important because you need those to be stable so all the combinational logic can settle out to the next value, right? And an n-bit flip-flop is just a collection of these single circuits, and all the clock signals are wired together, and there's a separate data input and a Q output for each of them. So by convention, we use D to mean the data input of a flip-flop and Q as the data output of a flip-flop. That's just the notation we use. And this is called a D-type flip-flop. So a D-type flip-flop is edge-triggered. So when the clock signal rises, it can be on either edge. Normally, we'll use positive edge-triggered in the class. So when the clock rises is when the snapshot is taken. So if you look at the waveforms of one bit of flip-flop, here's the clock here going up and down. Here's some data input. This is the input to the flip-flop. And this is the output. So say initially I don't know what the value was. It's undefined. I don't know what it was before. I'll just draw it as this gray box. It could be either a 0 or a 1. But after this clock edge, I know the output is going to reflect the input before the clock edge. So D was 0 here. So when I clock it, I copy 0 to the output of the flip-flop. Q goes to 0. Now notice in the middle here, I raise the value on D. I change D to be a 1, but the output doesn't change. Right? The output will remember the value it saw at the last clock edge, and it's not going to be affected by any change on the input. Right? The only time it changes will be the next clock edge. Right? So on the next clock edge here, then the flip-flop samples its input and produces the output here. Okay? And similarly, drops here, and it only drops. Although the data input drops here, the output only drops after the clock edge samples the input here and drops it down. So notice there's a delay. So once, this is a physical system, nothing happens infinitely fast. There's some finite time for this action to take place. So after the clock edge, it takes a little while for the output to reflect the new input. And that's called the clock to Q delay. Pretty rational name. It's the delay from when the clock edge arrives to when the Q output reflects the new input that's been captured. And you see that there's just this delay from every clock edge. Okay, so notice here that the data input went up, then it went down again, but the output only reflected it didn't actually change because it was 0 at this clock edge, and it was 0 at this clock edge. The fact this went up and down is irrelevant to the output, right? So the flip-flop hides all the transitions except the ones right at the clock edge. Okay, so this is kind of important. This is how flip-flops work, or what they do. So there are real physical systems, and how you build them affects how fast you can run your circuit. And there are these 3 important timing parameters for every flip-flop. the way the flip-flop works, it needs a window of time in which the input is stable, right? So a little bit of complexity inside the flip-flop circuit, but it can't do its magic unless there's a period of time when the input is not changing. And that's defined by two parameters, the setup time and the hold time. So setup time is just the time before the clock edge, the data has to be stable. And the hold time is the time after the clock edge, the input has to remain stable, right? So the flip-flop will only operate reliably if your signal doesn't change within this setup and hold time window. It's just like taking a picture. You don't want people to move while the shutter is open. It's the same for the signal being captured by the flip-flop. You don't want the signal to move while the flip-flop is doing its sampling, right? So there's this window. Yep?
So I understand why that might be, but why isn't it that you would want to reduce that amount of time so you get more?
Yeah, that's a good question. So why wouldn't you want to make setup and hold time as small as possible? The answer is you do want to make it as small as possible. So the people designing the flip-flops, one of the things they try and do is reduce the amount of time, but there's fundamental limits to how small you can make that and have the circuit still work reliably. And so, they do the best they can, but there's always going to be some finite setup and hold time, right? But yes, you try and make it as small as possible. Right. Yep.
What do you mean when you say input data stable?
Right. The question was, what do I mean by input data must be stable? What I mean is it's either a 1 or a 0. It doesn't go up and down. It stays at whatever value it has for the whole duration. So if you're a 1 at the start of this window, you have to remain a 1 till the end of this window. You cannot sort of move around. You have to stay put. Just like a photo, you have to stay put while the shutter's open. Right? Otherwise, it's not clear what the value will be captured. Right? Question?
So is there a way it prevents it from changing in that time between setup and hold, or does it throw error?
Right, that's a good question. How do you stop it from moving in that window? One of the ways is that it's more a constraint on how fast you clock it. So what you have to do is make sure that the time in between clock edges is long enough that the circuit, the combinational logic in between the registers settles out. Right, so that's the notion of a critical path. You have to wait until all the outputs of your combinational logic have settled down. Remember, the inputs are being held by the registers. They're not changing in between clock edges. So everything's stable at the input side. Those signals are propagating through all that combinational logic you have, and ultimately they'll settle down to a value at the output. And you have to wait for that to happen. When that occurs, then you can sample it at the next clock edge. So basically what this means is this constrains how fast you can clock the system, right? The reason why the input may move up and down before the flip-flop, while the flip-flop is sampling it, is you tried to clock it too fast, right? The circuit hadn't settled down, you tried to sample it, but actually some signal was still propagating through that would change the value, right? So you have to wait until it settles down before you sample it. Question?
Is the rate at which it converges, in between from the signal to the actual output, is that proportional to how much, how many days and how many?
Right. Yeah. So I'll actually talk about that a bit later today, but the time it takes for the circuit to settle down is proportional to how many stages of logic you're propagating the signal through in the combinational logic. So how deep did you make the logic nest from the inputs to the outputs? So that's going to affect how long it takes the outputs to become stable, right? So yes, that's and as designers, that's one thing you get to control, is if you want your system to go faster, you put less stuff between the input and the output, so the signal will propagate faster. And that's a design thing you do. And you'll see this as you do the logic design project, how you can move the logic gates around and make the system go faster. And that's what the engineers at Intel, for example, they spend a lot of their time trying to do that to get up to these high clock rates. Okay. Question? How is the input data generated? So the input data, in one of these big systems, the input data is coming from some other register. So if I look at this, let's go back. This is sort of a generic picture of any system. So for this combinational logic, some of the inputs are coming from other registers, and the outputs go to registers. These other inputs may be from other registers somewhere else in the system or from some other combinational block. By far, nearly all the inputs are from inside the circuit itself, from some other register or from some register going through some logic on the way to this block. So most of the inputs and outputs are sort of internal to the circuit. Just at the very edges are sort of the ultimate inputs and outputs of the whole circuit block, right? And it depends on your context where those are going to come from. But within the circuit, nearly all of them are coming from some other register or some other combinational logic block within the circuit itself, right? Okay. So we talked about two of these parameters for the flip-flop operation, the setup time and the hold time. And so we said the signal, you have to wait until the signal settles down because it's not allowed to move during that period. The other parameter is this clock to Q delay. So, and this is specified from the clock. All three of these numbers are specified relative to the clock edge. So the clock to Q delay is from when the clock edge happens, when does the output appear, right? So how long does it take for the output to show up on the output of the flip-flop, right? And all these numbers are worst-case numbers, right? You might get away with violating setup and hold in some cases, but not in all cases. The clock to Q delay is the worst case. You know, like if the output was a 0 and you sample a 0, clock to Q delay is going to be nothing because it's just going to stay 0, right? It's only when it's moving from a 0 to a 1 or 1 to a 0 you worry about that clock to Q delay. But when you're designing a circuit and you're trying to run it at a certain clock rate, you have to make sure it works for any data value, right? So regardless of the data values, I have to go and meet my clock cycle time, clock frequency requirement. So there's these three numbers: setup time, hold time, which is all about constraints on the input when it can change. And then there's clock to Q delay, which is how fast does the output appear after I hit the clock edge. Okay. So this is just this camera analogy. So, you know, setup time and hold time are this thing about relative to when you press the button, you know, from how long before that and how long after that is your subject supposed to stay still. Click to data is really from, you know, when you click the button on the camera, how long does it take for the display in the back of the camera to show the picture you took? Right, that's kind of like the clock to Q parameter. So let's go look at the accumulator example. So one thing that we didn't mention before is this register, we're going to have a reset input, which is another wire coming in from the side. And when you raise reset, it's just going to clear all the bits in the flip-flop to 0. That's how you initialize it to 0. Right. There are different ways of doing it. This is one way of doing it. So here's the clock signal. So after every clock edge, rising clock edge, after a short delay, you're going to get the new value of the sum appearing here. So, you know, it's going to be 0 after this clock edge. After you hit the reset, it's going to be a 0. After this clock edge, x0, then x0 plus 1, and so on. Right? There's this clock to Q delay here between this clock coming in here and the data appearing here. Right? So this clock edge here and the data appearing there. When the data appears here, it kind of goes through, propagates around into this circuit, propagates through this circuit, and sets up the next value, right? So x0 is here on the output of this register. xi is showing up here. These two are being processed by this adder circuit. And after a while, this value here, si, will assume the value x0 plus x1. Notice that from when you change the inputs to the adder to when the adder produces the correct value, there's some time delay here. So this delay between here and here is the time to get through that adder circuit. And that'll depend on how you built your adder. So you can build fast adders, slow adders. You know, it depends how good a job you did designing the adder, how long it takes for this signal to propagate through there. Then you have to make sure it's got through and set this signal up, and that this signal is ready for at least the setup time before you try and clock it again with the next clock edge, right? So the setup time, you know, make sure you've got through the adder and everything's ready. Then you have to wait for the setup time before you can raise the clock edge over here. So in reality, when these things, they don't quite look quite that perfect. When they, you set up x0, x1 arrives here, they don't this adder will not instantly change from holding the previous value to the next value. If you think about the logic circuit design, there's lots of gates inside the adder. We'll get to how you build that later today. And each bit of the output is going to take a different amount of time to settle to the correct value. So it's going to be a midpoint where the output's just garbage. Like it's just sort of each bit is transitioning between the old value and the new value. And on these sort of timing diagrams, we just show that as a grayed out box, which is the case. We don't really know what the value is. It's some indeterminate intermediate value while things are switching around. But finally, it will settle down to the x0 plus x1. Okay. Okay, so now we kind of know enough to figure out how do we calculate how fast we can clock a circuit, right? So any circuit, in fact, every digital system you can kind of draw like this. You just take all the combination logic in the system, put it in a big bubble, take all the registers and just put them all together as one, and then you can figure out what's the maximum frequency. So the maximum frequency is just 1 over the period, 1 over the maximum time you have to allow for the circuit to settle. So that includes the time to propagate through the logic, the time to set up the register, and the time for the register to produce the next output to feed in the next cycle, right? So all those three things happen in series in the circuit, those three timing delays, right? So the period, max delay of this circuit is given by the clock to Q delay. So if you look at it starting from one clock edge arrives here, takes some time, clock to Q delay for the data to show up here for the next cycle. Then you have to propagate through the combinational logic, that's the CL delay. And then once that's stable, you have to wait the setup time before you can clock it again. Right? So those are the three components of the cycle time in this system. Clock to Q delay, combinational logic propagation, and setup time before the next clock edge. Okay. Now, as a designer, you want to minimize the critical path. You want to run at the fastest clock rate you can. And there's this notion of a critical path in your circuit. If you build a logic system and you look at how it runs, you'll see, wait a minute, everybody else has settled down, but there's one path that everybody has to wait on, the worst path. That's what we call the critical path because it's the one that's setting your timing. So good designers will look for critical paths and try and do something about them, rearrange the logic to reduce the time there. But there are some other tricks we can use. And one of the ones just show you here, this is looking ahead a little bit to later in the class. But say you had a system look like this. We had a register with two values in. Notice this little dash indicating these are multi-bit values. So I'm adding them together. Then I'm going to shift them. Then I'm going to capture the result here, right? So notice that the propagation delay from this register to this register goes through two of these combinational blocks. The signals just flow through the combinational blocks. And so the time from, how is this drawn? Inputs arriving to the output, inputs arriving here to the output settling here. So that's these inputs here to the output here. This delay here between here and here, between the input showing up and the output federation I having the right value. This is the sum of these two propagation delays, right? That could be a long time. If you want to speed this up, clock it faster, what you can do is add a register in the middle, right? So you have this wave of computation for one set of inputs coming through. Instead of waiting it for it to go through both stages and then clocking it, let it go through one stage and then clock it. Then you can send a second wave to the first stage while the first wave propagates through the second stage, right? So this is called pipelining. So I send in inputs here. They only have to get through to here. Then I add a new register here, which holds this value, right? And then in the second step, I go through these two. So I can almost double the clock rate here of this system because I broke it up, that long combinational logic block, into two separate combinational logic blocks separated by a register. So I kind of move in smaller steps, and therefore I can raise the clock rate. And so this system will actually run nearly twice as fast probably as the earlier system in terms of clock frequency. Right? So that we could call this a higher bandwidth system. It produces more outputs per unit time, right? Propagating through the system. The one downside of this system is it might actually have somewhat greater latency. If you timed how long one pair of inputs propagated through this, it would take slightly longer to get from end to end. So why is that? Sorry? Right, exactly. So you've added a register in the path, So getting from here to here, you now have to go through this register, and there's a setup time and a clock to Q delay going through that register. So the time, if you just look at one value propagating through, it's got a bit longer. But the great thing is now you can put, when you have independent computations, you can do multiple of them, pipeline one after the other, and improve the rate of the circuit. Right? So this is an example of the other great idea in computer architecture, which is parallelism. So while one set of input is up here, the other one is down here, and they're both propagating through the system. So things are happening quicker. Okay, just to recap over these, I'm sort of hammering this home because you really need to know this stuff. The clock is a steady square wave that synchronizes all the registers, which is global to the system. Setup time, time before the clock edge, you have to be stable. Hold time, the time after the edge, you have to be stable. Clock to Q delay is how long it takes the new value to appear on the output of the flip-flop after the clock edge. So flip-flop is one bit of state, and a register is multiple of those, or one or more of those bits in that work together. All right, let's see if you got that. So clicker time. So just to explain this a little, here's a little circuit. These are AND gates, and the delay of each of those AND gates is 1 nanosecond, right? So the AND gates are combinational blocks with 1 second delay. You have the other parameters here. So what's the maximum clock frequency of this circuit? Oh, let me turn the thing on. Okay, let's take a look what people are thinking. All right. So I think this means you need another couple minutes to talk to your neighbors about this. Okay. Try and get your votes in. Okay. Okay. Still some confusion. All right. Let's go through this. So the way to do this is you start from the start of one clock edge to the next clock edge. And what's the longest path from getting to one clock edge to the next? So here's the register. So when the clock edge arrives, you know you have to wait at least the clock to Q delay before the output data is available to start things off. So you have 1 nanosecond before this value shows up. And where does it go? Well, it looks like the longest path is through these 3 gates. So this signal output here has to get through 3 gates before it can set up the input to the flip-flop. So if each gate is 1 nanosecond, you have to go through 3 of them in series. That'll be 3 nanoseconds. So there's 1 nanosecond for clock to Q, 3 nanoseconds of propagating through the AND gates, right? And then at that point, the signal will stabilize. But you can't do the clock edge just yet. You have to wait the setup time before you can raise the clock edge. So that's here, 1 nanosecond. So there's another 1 nanosecond on the end of that. So it's 1 nanosecond of clock to Q, 3 nanoseconds going through those 3 AND gates, and then 1 nanosecond to set things up. So there's 5 nanoseconds around that loop, right? So 5 nanoseconds is 200 megahertz, right? So, yep. Okay, so question is, why don't you have to go through this one as well? So remember, circuits do everything in parallel, right? So everything is running all the time. And this is not a critical path. This is a different path, right? So this signal doesn't change the output of this guy, right? So wherever this was, it's going to settle very quickly and not influence the output here. This is the path that's going to be the critical one. Right, question? Why doesn't the hold time affect the max delay? Good question. Hold time doesn't affect the max delay because it doesn't change. The clock to Q delay tells you how far after the clock edge this thing appears. The hold time just tells you that the input can't change that far after the clock edge. Right? The hold time doesn't actually factor in to critical path analysis. Where the hold time comes in actually is to make sure your circuit is correct. If you had just 2 registers where the clock to Q delay was less than the hold time and you put them back to back, the signal leaving the one register would get to the other one before it finished sampling the previous cycle, and your circuit would break. So hold time, we're not going to cover that just yet, but the hold time is important for a different reason. It's actually for fast paths, where you have a signal that propagates too quickly. And so you kind of have the next value appearing before it should, before you've had time to capture the last value, right? But the hold time doesn't affect the critical path. So just work through this again. So when the clock edge arrives, the signal appears clock to Q time after that. You just need to find the longest path through those AND gates. All the other paths are happening in parallel to the longest path, so they don't change it, right? So it's a parallel circuit. All the other things are happening at the same time. It's just the longest delay from an input changing to an output changing you have to worry about. In this case, it's this signal here going through these 3 sequential gates and setting up this input here. And then when that input is ready, you still have to wait the setup time before the next clock edge. Right? Question?
I feel you, but like when you feed it into like the other like AND or op amp, whatever you want to call it, you need to wait for the other guy because they're both feeding into the same app. So why don't you have to? Because that's just one leg. So is that one always getting like a little signal?
Right. Remember what's actually inside these symbols. right? Those switches, those transistors. So what's happened is, like when this signal shows up here, all the switches it controls are thrown the right way. So the switches just set, they're ready to go. And the output will have some value, right, depending on what this guy had before. So that signal, once it arrives, it's done its work. It's kind of set all the switches the right way. The second signal arriving will just flip the remaining switches that it controls and then change the output. Right? So just think about it that way. There's all these switches inside these gates. The signal that arrives, if the signal arrives first, it doesn't have to wait for the other one. They're actually not coupled in any way. Each input signal independently throws all the switches it controls. Right? And then the second arriving signal just has to throw the switches it controls and to cause the output to be connected to, +1 or 0. Right? Any more questions? Yep. Yeah, the question was, during the setup period, is the flip-flop doing anything? Well, actually it is. So the flip-flop is a more involved circuit, and part of the setup time, that represents the time it takes for the input to the flip-flop to propagate through the circuitry inside the flip-flop, and to actually create a stable value inside the flip-flop, such that when you raise the clock edge, it does the right thing. So I don't think we're going to cover how you design a flip-flop in this class. If you go to take 150, we'll go over how to design it. It's not a trivial thing to design or think about. It's not that hard, actually, to do a simple one. But for now, just think about it as the flip-flop needs some time internally for its own circuitry to do something. That setup time gives it time to do the right thing. Similarly, the hold time is there to make sure it is stable, so it doesn't flip back to the old value. It just gives the internal circuitry time to set things up. Yeah. So the flip-flop itself is just built from some more switches. In fact, it's just built from, you could build it from NAND gates. You could build it from, but it's all just another set of switches and circuitry that are doing things. Right? Question?
Yes. The one I think, but how did we get from 5 nanoseconds to 200 micrometers? Like, what is it?
You take the reciprocal, right? 1 nanosecond is 1 gigahertz, right? 10 to the minus 9. So, 1 hertz is 1 second, right? Right. That's really sort of high school physics. I'm sorry, but that's high school physics, right? I didn't go to high school. I grew up in the UK, so we did it in like infants, or middle school. But it's no, I'm serious. Yeah. Okay. Quick poll. How many of you haven't seen time going to frequency before?
No one's going to raise their hand.
Right. So you all have, right? So, yeah, I mean, it is just basic physics, right? Inverse of time is frequency. And I believe it is high school. If you look at the whatever it is, I'm pretty sure it's on that level. Yep. Yeah. Well, actually, let me finish this one first, and I'll come back over. So how do you actually do it? So 1 second, something that beats at 1 time per second, 1 cycle per second, that's 1 hertz, right? And the period there is 1 second. So 1 second in between beats, 1 cycle per second. You 2 cycles per second, that's 2 hertz. That's half a second, right? So clock period is inversely related to frequency, right? So the hertz is how many per second. The units are just flipped around. So you just divide 1 over. So 1 over 5 nanoseconds gives you 200 megahertz. 1 over 5 times 10 to the minus 9. Take the reciprocal of that. It's 200 million. And the units are megahertz, right? The units are hertz. So time and frequency, they're just inversely related to each other, right? Sorry. Yeah. Sorry. I realize you probably all had this, but just forgot it because you never used it. Is really what happened. You all did actually take the class, just using it in practice. Yep. How I got 5. Okay, yeah. So this is actually the harder thing about. I'd expect to be the harder thing is understanding what happens at the same time versus one after the other in the circuit, right? And this is actually difficult for a lot of people to get. Well, just think about what's going on in one of these boxes. So this box is just a collection of switches, as we talked about last lecture, right? So an input signal comes in, and as that voltage changes from 0 to 1, it's just opening and closing switches inside that logic gate, right? So this signal says, some subset of the switches are open or closed. So that's what's happening. As it does that, it generates, a new value on the output of this guy, which in turn will set the switches in the following guy, right? The thing to worry about is what are the dependencies? What depends on the previous level of logic and what doesn't? So, for example, this signal here will change the switches in here, which will change the output value here, which will change the switches in here, which will change the output value here, and so on. And so you have to wait for that process to complete, where the first guy sets the switches, which sets the output value for the next guy, which then changes the switches in the next guy, and so on, right? So this leg, this kind of arrives earlier. These switches are all set up. This signal arrives. The switches that this signal controls are set up ahead of time. So this path doesn't impact this overall delay, right? This overall delay, when do I know how to set the switches on this input? It's after it's propagated through that whole other network. So each signal propagates independently through the circuit. And this is all happening in parallel. And you're just looking for the longest path. What's the longest chain of events before the output settles? And that gives you the critical path. Right? Yeah, no, so it is a big transition from, in most software we teach you how things happen one at a time, sequentially when you write the program. And when you're reasoning, most people's conscious reasoning is pretty sequential. When you're actually consciously thinking of something, you go step by step in your head, right? And circuits don't work like that. They work like the other part of your brain, the unconscious part of your brain, where everything happens in parallel. And it is a difficult thing to sit and reason about. And that's why the hardware design is often very frustrating, because stuff happens kind of behind your back. You didn't think this would be changing over there in that part of the circuit, but it does. And remember last time I showed you that waveform diagram, all the different signals, and everything's changing all at once. Yeah, but the way to systematically do this is to start at the registers, look at the outputs, and just trace, what's the depth of this? How many stages of logic does this go through, and how long is each stage? Right, that's the way to systematically do it. This takes, 1, 2, 3 steps to get to here. This is just 1, 2 steps. And also these inputs they're just sort of out in space. So you just assume they've arrived in time. Right. So you're looking for the longest chain of events in each clock cycle, and that gives you the critical path. Well, so actually, that's a good question buried in there, which is, why is I said the maximum clock frequency, right? You don't have to clock it at 200 megahertz. The circuit will still work if you clock it slower than that, right? So it's the maximum because if you imagine having a knob that you turn that you're turning up the frequency, how fast can I make this thing go? At the slower frequencies, everything's fine as well. Right, the signals will arrive in time. There's plenty of setup time. There's no problem, and you just turn the knob to compress the the cycle time and make the edges come closer together. And at some point, you won't meet the timing. Like the signal will take too long to propagate and it'll break. Another thing to realize is that depends on the data values. So if, for example, all these bits were 0, none of the wires would be moving up and down. Everything would be staying 0. And you think, oh, this is great. I can run this at 10 gigahertz. It's still working. But it's not actually doing anything, right? Nothing's toggling. So the maximum clock frequency is for the worst case where the data values are moving around. Right? So it's the worst case propagation delay in the circuit. A question?
Could you just point out where all the clock to Q setup in the circuit?
Okay, so let's go through where these parameters show up in the circuit. So clock to Q shows up here. So the clock arrives, and it takes clock to Q delay before the data shows up, right? The signal propagates around. The time to get through one of these AND gates is 1 nanosecond. So that's the time it takes from when the signal arrives, all the switches are thrown, and the output signal changes. That's that delay. That's the 1 nanosecond there for each of these stages. Right? So after this 1 nanosecond, this output is ready. Then after another nanosecond, this output is ready. After another nanosecond, this output is ready. Then you arrive here, and once the signal's got to that point, you still have to wait another nanosecond for the setup time, right? So 1 nanosecond before this clock edge is the setup time for the flip-flop. So everything has to settle down, and then you have to wait another nanosecond before you send in the clock edge, right? And as I mentioned before, the hold time doesn't factor in here. All the hold time tells you is that after the clock edge, this better not change for 1 nanosecond. And in this circuit, that's kind of guaranteed because none of these inputs can kind of get here more than, they have to get through a couple of gates before they arrive here. These outputs, this already has 1 nanosecond of delay before anything appears on the output here. So you kind of know you're not going to violate this hold time, right? But I thought the hold time doesn't factor into the critical path. Okay. All right. Okay, so give you a bit of a break by looking at administrivia. So project's due on Sunday. The midterm is a week from today. It covers, this is wrong, covers everything up to the 2 lectures ago. Okay. You'll add 1 cheat sheet. We'll give you the MIPS, the processor description. There'll be 2 review sessions, Monday and Saturday, in Evans and in GPB. Okay. So let's keep going. So let's talk about what you build with these. So we kind of talked about the basics of building a circuit, the sequential piece and the combinational logic piece. And one of the things you build in digital design are called finite state machines. And you should have seen these in other classes, right, in the software classes. So what's a finite state machine? Something that has a finite number of states and just moves between them according to some transition function, right? So you draw this as this kind of diagram. Here's the states. Depending what shows up at the input, I move to different states and produce some output. Hopefully this is familiar from the earlier classes you've taken. So let's do a hardware design of one of these. And now I'm going to build a hardware circuit that implements a finite state machine. And in particular, we'll take this little example, which is a circuit that detects 3 1s in a row appearing on the input, right? So you have some input signal coming in. Every clock cycle, you're going to sample the input. And when you see 3 1s in a row, you want to output a flag saying, I saw that, right? So here's some input. This is the output. So I just saw 1 1, no good. 2 1s, no good. 3 1s, yes, I want to put an output out. 4 1s, I want to put an output out, etc. Right? So this is our spec. Now, if we draw the state machine, it looks like this. So every time I start in the S0 state. Every time I see a 1, I move over. If I see 2 1s and 3 1s, this is 1 1, second 1. On the third one, I go back to the start and I output a 1, right? So The notation is the input, then the slash, and then the output, right, on the arcs, right? So when I see a 1 on the input, I produce a 0 on the output here, 1 on the input, 0 on the output here, 1 on the input, I put a 1 on the output here and go back to reset to the state 0. If I see a 0 in state 0, I just loop back and do nothing, output a 0. Along the way, if I'm moving along here, but then I see a 0, I go back to reset, okay? So that's the specification for the state machine, what we would like the hardware to do. And then we can think about building this. How do we build this state machine? So break it in two pieces, the sequential piece and the combinational logic piece. So the sequential piece is some register bits that are holding the state you're in. So that state is held in the registers. And on every clock cycle, it's going to advance to the next state. And then we're going to say that the output of the register is the present state, and then the input of the register will be the next state coming in, right? The combinational logic is going to take the input signal and the previous state and generate the output and the next state. So if we put it all together, this is the circuit. So the input comes in, goes to the combinational logic, is combined with what state you're in to produce the next state, and also produces the output from here. And then the clock happens there. Right, so this is the hardware realization of a simple finite state machine. So if we just dive into the combinational logic piece part of this, and we just have to write out a truth table now saying, what does it need to do for every combination of what state am I in, what input arrives, what next state should I produce, and what output should I produce from there. So the truth table, these are the input, this is the input side, and this is the output side, right? So notice one other thing I have to do is do an encoding of the state. Right, so abstractly on this diagram, I just call this S0, S1, and S2. So how many bits of register do I need to encode this, to hold the state? 2. So I need 2 bits of register because I have 3 possibilities. Right, so 3 possibilities I can encode in 2 bits. There's a spare one, but that's okay, spare encoding. But I need to actually pick which encoding I use, so which pattern of 1s and 0s, 2 1s and 0s represents each state, right? And if I just do the simple thing, I'll encode state 0 as a number 0, state 1 as a number 1, state 2 as number 2, and there is no state 3, even though I could, in the registers could represent a state 3, right? So that's the 2-bit encoding of which state I'm in. Then for every state that I'm in, or every input that arrives, I can list what should the next state be, right? So if I'm in state 0 and I get a 0 on the input, I remain in state 0, then produce a 0 on the output, okay? And if I'm in state 0, I get a 1 on the input, I move to state 1, but still have a 0 on the output. So going through this, the only case where I produce a 1 on the output, if I'm in state 2 and a 1 shows up, I go back to state 0 and produce a 1 on the output. So this is a truth table for the combinational logic. So this is just a piece of circuitry that you set the input signals up correctly, all the switches are thrown, and eventually the right output values show up on the output of this logic block. But you need the other piece, which is a sequential logic element, the actual register that's clocked to actually move to the next state. This is just calculating what the next state should be, right? So this is just saying how to build this circuitry here, right? I also need this register that takes that value and on the clock edge actually advances the machine on to the next state in the diagram. It actually takes a step in the state diagram. Okay? Does that make sense? Any questions about that? Okay. So we've specified the state machine using this truth table, and that's a complete spec. That tells you everything you need to know about how to build that logic block. And there are many, 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 many ways of implementing that logic block that has this specification. And as we talked about last time, you can take that truth table specification, turn it into a logic expression, and then minimize it to cut down the number of gates you need to build that. And actually, you can easily move between all these different representations, right? So truth table, you can turn into a Boolean expression. You can actually go backwards from a Boolean expression, fill in the truth table. If you have a Boolean expression, you can simplify it and then translate that into a network of gates, like basic logic gates, ands and ors and nots. If you have a gate diagram, it's easy to go back to a Boolean expression and so on. If you have a gate diagram, it's also easy to fill out a truth table. You can actually go from a truth table to a gate diagram, but usually that's a little bit of an awkward set of gates you get out of that. You'd have just basically one gate for every row in the table. So hopefully from last time's lecture, you kind of realize how to take a truth table, turn it into a logic expression, and then manipulate it to get a simpler set of gates to implement the function. All right, so let's move on to the next part of the class. So over the next few lectures, we're going to be telling you how to build a computer out of these logic gates. And you don't sort of write one great big truth table that's the whole computer. You break it down into some kind of structure of some components that are connected together, and then you design each component individually, sort of divide and conquer approach to building the whole computer up. And so today we're just going to focus on some basic combinational blocks that you're going to need inside your computer, right? In particular, a multiplexer, arithmetic and logic unit that actually does addition and logic operations, and the adder subtractor lives within there. It actually does the adds and subtracts. So let's start with a basic building block. It's called a data multiplexer. MUX is what logic designers call this, a MUX, a multiplexer. So what does a multiplexer do? You have two inputs in this case, A and B. They may be multi-bit. This is n bits of input. And you have a select signal that says which one of those inputs you want to have appearing on the output. So this is kind of a selection operation. Pick one or the other and send it to the output under the control of this signal. So it's typically drawn as this kind of shaped box with inputs on this side, output here. And the inputs are sometimes labeled with the value of the control signal that will cause the corresponding input to be reflected on the output. So in this case, if S equals 0, A will appear on C. If S equals 1, B will appear on C. So that's the functionality of the MUX. So this is a two-input MUX. It has two inputs being MUX to the output. But it's also n bits wide because each of those inputs contains n different signals, n individual bits. Okay? So the way you build an n-bit MUX is you take n copies of a 1-bit MUX, right? So take this guy and just repeat it n times. So again, this is divide and conquer. I now have to only worry about building a single MUX that is 1-bit wide, okay? Because I know I can just take this and parallel it up to build an n-bit wide MUX. So if this is just a combinational logic block, so I can always write out a truth table expressing its functionality. So how many rows in the truth table are there for this 1-bit MUX? First of all, how many inputs are there to this 1-bit MUX? No, not 2. 3, right? There's A and B and select. Those are the 3 inputs to this function, right? How many outputs? 1, right? So there's 3 inputs and 1 output. So how many rows do I need in the truth table? 8, right? 2 to the 3 rows. So there's 3 inputs. I need 2 to the 3 rows to specify. So I need 8 rows in the truth table. And there they are, right? So select is an input. A and B are inputs. Just step back a moment and think about this. You all said 2. A lot of you said 2 for the number of inputs. That's because you're thinking, it's a 2-input MUX. Remember, the logic circuit doesn't know what you think it is. It just, it does what it does. It's really are those signals coming into the block or leaving the block is all you need to think about. The fact that one of them is a select, one of them is A, and one is B, that's just your interpretation of what the circuit does, right? But they're all input signals. So for each input signal, for each of the rows, we just lay out the combinations. So notice here, when select is 0, A should be propagated to C, and so the values in the A column are just copied to the C column. And notice B has no effect, right? Doesn't matter what B is. If 0 is 0 on S and A, whether B is 0 1 doesn't change. Like C always has a copy of A, right? And conversely, if select is 1, you're copying B to the output of C and ignoring A. So that's the function of a mux. Just select one of the two inputs according to the select signal and propagate it to the output. So this truth table is now just a logic function that you can go optimize however you wish. So we can just translate that directly into a logic expression. Notice here what I've picked out is, remember this sum of products form. Look at all the outputs that are a 1. Look at the input combination that generates a 1, and all these rows together, they generate a 1. So this row that generates a 1 is not S, A, and not B. So it's not S, A, and not B. That generates a 1. Or this row, which is not S, A, and B. So not S, A, and B also generates a 1. So this is how you go from this truth table to a sum of products expression. That's not very optimal usually. You then want to go simplify that down, which is what happens here. If you go through the steps, you end up with this. Basically, what you might expect, if select is 0 and A is true, you want a 1 on the output. Or if select is 1 and B is true, you want a 1 on the output. In every other case, you want a 0 on the output, right? So it's actually a pretty simple function when you simplify it down. Right? So there's the logic expression. So what's the circuit look like? Well, here's a way of building it using logic gates. So this is the expression. So here's S. So this first part is not S and A. So I take S, run it through a NOT gate. This will be not S. Here's the A input. So not S and A. That's this component. S and B is just S and B going through an AND gate. And then the OR symbol is just the last piece here going to C. So there's the circuit diagram for a simple 1-bit mux. Okay, built out of logic gates. Okay. Any questions about that? Yep, question? Yes. Right, so the question was, what if you have more than 2 inputs? You have 3 or 4 inputs. We'll actually get to that in the next couple of slides. Any other questions? Okay. So here's answering your question. Say I had 4 inputs, right? So this is one multiplexer that has 4 inputs. And notice, because I have 4 inputs, I need more select signals, right? So I need different combinations to select this. So now I have a 2-bit select signal, S1 and S0. And these are the 4 combinations that select one of the 4 inputs, right? So now, depending on whether the select signal is 0, 1, 2, or 3, I'm going to select one of those 4 input signals and copy them to the output of this combinational logic block. Okay, so how do we build this? Say we wanted to build a truth table for this. Well, first of all, how many inputs does this combinational logic block have? Has 6 bits of input, right? So how many rows does the truth table have? 2 to the 6, 64 rows in the truth table. That's kind of big. You could do it that way. But if you did, it's much easier just to go directly to the logic expression based on what we did last time. Well, what I really need to do is, if the 2 bits are 0 and A is a 1, I want a 1. If this combination of S1 and 0 and B is a 1, I want a 1. And similarly for the other ones. This is actually the simplified expression. You can sort of skip the truth table if you can follow that pattern, right? Select bits and the input is 1. I want a 1 on the output. And similarly for each other combination, the relevant input, right? So that's one way to build a mux. You can just take this expression and turn it into gates. But an easy way to do this is actually to say, well, I already built a 2-input mux. Why don't I just reuse that component? If you think about competitions, right? Tournament competitions, you can build a 4-input mux as a tree of 2-input muxes, right? Hierarchically. So this is a general idea, right? So now I've got my 4 inputs over here, A, B, C, and D, output E. And notice what I've done is I've paralleled two input muxes here, and they both connect to S0. So I'm selecting either A or B or C or D at this intermediate nodes, and finally use the high bit S1 to pick these two or these two to give me the output, right? So, this is saving effort. I've already built the two-way mux. I just warp a bunch of two-way muxes to give me a four-way mux, right? So I can do it either way. I can build it directly as a 4-input mux, or I can just cascade 2-input muxes together to get this guy, right? So now the question you should be asking is, well, which one's better, right? Which one's better? Should I do it that way or that way? And the answer is, it depends, right? In your technology, how many logic gates does each way take? How big are the logic gates? How slow are they? What's the critical path through doing it these two ways? How much time do I have to finish my project? Might influence whether you just reuse a component you had or tried to build a custom one that just to fit this need, right? So in general, all these questions you would ask, about which one's better. Okay. So that mux block, so this mux is a very, very common component. So I would say in microprocessor design, it's the most common thing you have in a processor apart from flip-flops and registers. So basically, registers and muxes are probably 80-90% of any computer are just registers and muxes, right? That's what they're built from. In addition, you kind of have a few blocks that do more interesting things like add numbers together, right? But it's surprising how much of a computer is just registers and muxes. But anyway, at the heart of the CPU, you have what we call the arithmetic and logic unit. And this is the thing that actually does the compute in your MIPS instructions. Your MIPS instructions have add instructions, subtract instructions, shift, and, or, XOR. Those kinds of operations, the ALU is where these things take place. And the ALU is in particular where the arithmetic and logic operations take place. That's where the name comes from. And we're going to show you one particular design that does add, subtract, and logic operations. In this case, it does A plus B. Here's A and B, 32 bits wide. A plus B, or A minus B, or A and B, or A or B, where these are the bitwise and the bitwise or you've seen in the MIPS instruction set. So how do you build this? Well, one thing is notice it has a function input on the side, S, which selects which function you're doing. Right? So I'm going to build an ALU that can do multiple functions, and the way I tell it which one to do is by another couple of signals coming in the side, selecting one of those 4 options. So what do those select signals do? Well, they just drive a mux, right? They just select. What I'm going to do is have independent blocks that can do add, subtract, or an and then have the mux pick the right result and send it to the output. So here's A and B coming in. And there's one little optimization here. We're going to build instead of having a separate adder and subtractor, it turns out we can combine those and build one unit that does add or subtract. But we'll have a separate unit that does and a separate unit that does or. So this is a good point to go back and revisit some of these other questions about all these gates in the circuitry. When you input A and B to this combinational logic block, this block actually calculates all of those things at the same time. It's going to calculate add or subtract, and or. And all of those will be evaluated at the same time. Your circuit's going to do all the work for all 3 of those operations, regardless of which one you pick at the output. The circuitry doesn't care. But just think about what's going on. I set up my A and B inputs. I set up my select signals here. These A and B signals turn all the switches on in here, turn all the switches on in here, turn all the switches on in here. And that just all happens in parallel. It doesn't matter that you're not using one of them, right? It doesn't matter. You just flip the switches, and and every time you use this block, you're going to calculate the and of the signals, the or of the signals, and add or subtract of the signals. Every single time, all 3 things are going to happen. Yep.
There's no way of putting that before, so you can only turn on some of them one time instead of calculating all of them and selecting them like a select button.
Right. So the question is, well, isn't that wasteful to have all of them running all the time? Are they going to wear out? The answer is, it doesn't matter. So it's parallel circuits. So, and also they're solid state. They don't actually wear out, or very slowly. So it's fine to have all of them moving up and down, even though you're not using the output. The question is, why does it hurt to have all of them work in parallel? The answer, it actually doesn't. And you want to do this because it makes your life easier. Instead of trying to figure out how to stop one of them from doing something, it's easier just to let it do its thing and pick the output later, right? So all three of these blocks are going to work in parallel at the same time. And I just select the right one at the end that I'm actually interested in, okay? Now, there is one reason why you might not want them all to switch. Anybody know why that might be? Yeah, more power, right? So it turns out that these switches moving up and down, that's where the power dissipation is in a chip. So what you might want to do is find some way of turning off the ones that aren't being used, but then you need to actually add extra circuitry to stop it moving. And so to save power, you actually have to spend extra resources to stop it from moving. So in the simple design we're doing, we're just going to ignore the power piece and just move them all the time. Yep? Okay, so the question is, in one use of this, I have zeros coming in here, right? And they're driving the AND gate, and it produces a value at the output of the AND gate. And then the next time I want to use, I'm sending ones down there. What happened to the old result? Remember, the old result is just a value on a wire in the circuitry. So get back to what's physically happening. What's physically happening is when I change these signals, I'm just changing the switches, right? And so the output wires will change to 0 or 1. And kind of nothing happened. The output wires hold the values. When I change the input switches again, they'll hold a different value. Or just think back to the light bulbs. You have a couple of switches driving a light bulb. I change the switch, light bulb has one value. I could take a photo of the light bulb. That's my register, right? I then change the bits. The light bulb goes on or off. I take another photo of the light bulb. And if I don't take a photo of the light bulb, it's still going to shine on and off. But, all I'm doing is changing the input bits, right? So I think one common problem people have is they're so used to programming and software and variables, writing words in memory. They think hardware works like that, and it doesn't. This is just like, switches in the system. Just try and go back to the light bulb analogy. Might be an easy way to think about it. I set the switches, light bulb comes on or off. If I want to know what the value is, I take a picture of it, which is the register, right? If I reset the switches, the value changes. But moving all the switches around doesn't hurt the circuit, doesn't change what's going on. Doesn't change other parts that I'm not looking at, right? Okay, so just quickly at the end, for now, in the news, you might have seen this, but Microsoft and Google both announced that they can now, with their computers, recognize images better than humans, right? So this is kind of surprising if you've been following AI for a long time. Basically, what they have is a large set of images, and they ask humans to characterize them, and that's meant to be the benchmark. How well can you do? And they figured out by throwing millions of images at their large neural network-based systems, they actually have less errors than humans at categorizing those images now. They're just it's a tiny bit better than humans, but it is better, which is kind of surprising. Anyway, so your project will be based on this technology. So.